record. All right, we're at smallest node. I'm gonna clone this down. Clear, get clone, CD in the smallest node. I'm gonna open this into a new VS Code window. All right, go ahead and zoom a little bit. So we've got the smallest node. We already have like the code to create a binary tree and to insert into a binary tree. And we also have some tests written. I'll open that into a new window. All right. So when we have a binary tree, such as, where's this one? So 10, 5, 6. So if we have one that's like 10, 5, just visually 19, 1, 6, 17, and 21. All right. So this top one, that's the root node. So we always start at the root node and we traverse it. So something like that. Yeah, whatever. So we start at the root node 10, and we need to find the smallest node here. So I'm going to def find smallest. And in here, it doesn't say it passes in anything. If you want, you can pass something in here, or you can create like a helper function. I will pass something in here. I'll pass in the current node, or like the current node. And or pass in self dot tree dot root. So the current node, we're always going to start at our very root node and traverse down to the left, because we want to try to find the smallest. So we're starting at the root node. We're going to check, hey, does the root node have a left value? So does the root node have a left value? If it does, we're going to pass instead of 10, we're going to pass in 5 now into the current node. And we're going to check, hey, does the current node have a left value? Yes. All right, we're going to pass in 1 in here. Does 1 have a left value? No, it doesn't. Therefore, 1 is the current, the smallest value in the tree. So we can do this recursively or like functionally. So I'll do it recursively. Actually, yeah, I'll do it recursively. So first thing I'll do is if current node dot left, if that has a value, then or I guess I could say if not, is that one? If not current left, then return current node dot value. Else return find smallest. I guess it'd be self dot find smallest, and we're going to pass in the current nodes dot left value. And if I were to do that right, let's see. if I did Python test, maybe that's right. Yep. So that's one way to do it recursively. Did you, Devin, did you say you did it a little bit differently? Did it two different ways?
The second way that I did it, because the
Okay.
first way felt stupid.
Okay.
The first way I created a helper function to traverse the tree and just return an array that was already in order. And then I just returned array index 0,
Gotcha.
which
Yeah.
felt like it would not scale well at all. But
So we could also do this just functionally, but this is supposed to be doing recursion. So if we don't necessarily have to, if we're doing it just functionally, we don't really have to pass in anything. So we can start at, we can say that current node equals self.root and pretty much do the same thing. Or I'm sorry, current node value else. Here it is. Hold on. We would do while current node dot left does not equal none. The current node, I'm reassigning the current node to the current node's left. And then just return current node dot value. I think that's it. It's just functionally. Let's see if I could be totally wrong. So I just did that off the top of my head. Since we're not passing anything in this time. Clear. Yeah, still works. So this is, I'm literally just traversing. So the current node is the root. So while the current node left does not equal none, that means it has a value. So the current node is initially root, while the current node's left node has a value, does not equal none. So 5 does not equal none. I'm reassigning this current node to the current node's left value. So now current node is 5. So now the current node is 5. There's a current node dot left does not equal none. That is true because current node 5 has a left value of 1. So I'm reassigning current node to the current node's left side, which is 1. So does 1 dot left not equal none? No, because 1 does not have a left node. Therefore, we just return the current node's value, which is 1. Yeah. Any questions on that one? Anybody?
I have a few general questions.
Yep.
So index in Python or index of in JavaScript, that's linear search based, right?
I actually don't know.
Okay.
I'd have to look at the actual code that's actually going on within. There might certain functions, built-in methods like index of. I'm pretty sure it is linear based, but it might like after array. So I'm not quite sure,
Oh,
but
okay.
like if your input array is after a certain length, that index of might use a different searching algorithm to make
Okay.
it more efficient. But yeah, that's something that we'd have to like look at like index of Python time. Yeah. For elements. Yeah. Anyway.
So
did you have a follow-up?
Yeah, in the real world, do you find that a lot of companies, at least in contexts where efficiency is super important, are kind of rewriting index of solutions in a binary search format?
Yeah. So if, well, yeah, essentially they'll be writing their own algorithms instead of using built-in methods
Okay.
if it's important. Now, 99% of the time, it's not. It just depends on the position you're at, like working in, where it might matter. But to prefer perfectly candid, no. Like you rarely ever write your own searching algorithms. It's not. Yeah, it doesn't make a big difference.
Last question. Before I started this class, I did some leak codes and they referenced BinaryTree, and I just kind of skipped them because I thought it was like a data structure like arrays where it had its own syntax, but I didn't realize you like build it yourself. Are we going to get into like the details of removing nodes, binary trees, and all that?
Probably won't get. I don't think we're going to get into a lot of detail in data structures like binary trees and like breadth first search versus depth first search of trees, or hashes and hash tables and min and max heaps. Like we really don't get into that. The most we really talk about is like stacks, queues, and like linked lists. And then if there's time, we'll go into like binary trees or binary search trees. And like at most we'll talk about a hash table. But yeah, that's something you should, because a lot of these data structures like binary trees and all that, they do come up on, depending on where you go apply to, they do come up in interviews sometimes. So it's good to know them for interviews. But as far as like practical, like you'll never really use a binary tree in the real world. Like if you're a web developer, you're just not, like can't think of a scenario where like you need to know how to implement a binary tree to make your application work more efficiently. Yeah. It's more of just like a screening tool, these data structures, unless you're doing like hardcore computer science stuff.
Okay, thanks.
Yep. But it's good to know, and I think they're interesting. Yeah. Anybody else?
Unrelated, but just on that subject, because I was looking through it the other day. All of MIT's computer science courses are pretty much free, and they have several on algorithms and data structures that all look incredibly scary, but they're out there and free.
Yep. Yep. Open. What is it? Open. They're part of the. Yeah. It's all free. Like MIT stuff. It's on YouTube. You can also sign up for it. But that book, Cracking the Coding Interview, does a really, really good job at breaking down all the different data structures, as well as like questions to help you your problem solving when dealing with these data structures. So I've actually got mine right next to me. Well, you can't even see it because it's green. There it is.
Just add a +1 to that. I think I watched like the Beyond Tech from last Platoon where someone was coming in talking about the interview process, and he recommended the book. So I went ahead and ordered it, and I'm not very far in at all, but I can already tell it's very comprehensive, covering. It's just at the very minimum, it's going to make me feel very prepared for the interview, which for me, I like to be, that's where I derive my confidence, is by being prepared.
Yep. No, yeah. Yeah, it was written by she was like was responsible for hiring all Google early on, like all Google employees. She like wrote the book. Yeah. But most of the time, if you're just practicing like easy, medium, leak code questions, that's generally good enough to pass most technical interviews. But it's good to know what these data structures are and kind of how they work, and also why they even exist. Like, right. Any final questions? Nothing. All right. It is 9:28. Tomorrow, Chad's actually going to be lecturing. I've got a board meeting to go to, so I won't be in. But yeah, definitely reach out if you have any questions. Oh,